Look at this data stream. In a fraction of a second, this program generates a secure winning lottery ticket, calculates a dynamic prize pool, and analyzes thousands of historical records to find long-term trends. If you tried to write every calculation required to make that happen from scratch, you would end up with a single, massive Python file. As programs grow larger, cramming all your code into one place becomes completely unmanageable. The solution is to use modules. A module is simply a separate file containing pre-written Python definitions and statements. And thankfully, Python comes with a massive standard library of these modules that you can borrow from immediately. By utilizing this library, you avoid writing complex math and randomization logic yourself. You can build an automated lottery picker and data analyzer in minutes, simply by orchestrating the code that already exists. This interface shows our code editor on the left and our terminal on the right. Step 1 in building our analyzer is bringing our tools into the workspace. We start by typing two standard import statements, import random and import statistics. This graphic shows how standard imports work. We brought in the entire folder. To use a tool inside, you use a dot to link the module's name to the function. Now, watch how individual tools are pulled directly onto the workspace. For math operations, we type from math import square root ceil, removing the need for dot notation. This red warning overlay shows what happens if you use a wildcard, typing from math import asterisk. Pulling every single function into your workspace blindly makes it highly likely that two identical names will collide and crash your program. Deliberately controlling exactly how and what you import is your first line of defense against logic errors in complex projects. Let's write the logic to draw our winner. We create a variable called winning ticket, assigned to random.randint, setting our range from 1,000 to 5,000. This number line illustrates a critical rule for randint. Notice how the brackets clamp firmly on the exact numbers 1,000 and 5,000. Unlike standard Python ranges, both boundary numbers are inclusive and can be selected as the winner. Next, we add a print statement and run our script. Over in the terminal, our first randomized ticket number appears. Run the code a second time. The output dynamically updates to a completely different valid ticket. By utilizing a built-in pseudo-random number generator, we achieve immediate unpredictability without engineering complex randomization algorithms from scratch. Now we process historical data. We have a raw array named past winners, populated with several previous winning ticket numbers. To find the historical average, we create a print statement, utilizing the mean function on our data array. Look at the glowing dot in this code snippet. Because we used the standard import method in step 1, we must type statistics.mean to properly access the function inside its module. We do the exact same thing to find the most frequent past winner, writing a print statement for statistics.mode past winners. Executing the script now populates our terminal with two clean new data points, our accurate mean and our mode. The statistics module serves as a translation layer. It distills raw arrays of numbers into clear analytics using only 2 lines of code. For our final functional goal, we need to calculate a dynamic prize multiplier. This is determined by the square root of today's specific winning ticket. We define a multiplier variable and set it to ceil square root winning ticket. Notice what is missing from this line. There is no math prefix written before either function. Because we specifically use the from math import statement at the top of our script, the tools live directly in our namespace. The dot notation is obsolete. The square root function evaluates the winning ticket and generates the precise decimal value of its square root. As we see in this animation, the decimal is physically pushed upwards. The ceil function forces that exact decimal to the smallest integer greater than the current value, ensuring a clean payout. Directly importing specific mathematical functions gives you highly readable, elegant formulas that avoid the visual clutter of repetitive module names. Step 4. Clear your terminal for a final end-to-end execution of the script. Looking at this terminal window, our results are complete. We successfully generated a valid ticket, the average, the mode, and our rounded multiplier. This expanding foundation represents what just happened. Your 15 lines of code triggered a massive volume of underlying C and Python code running invisibly. For your next independent step, Open the Python documentation and search for random.choice. See if you can figure out how to pick a random winner from a list of names instead of numbers. You don't have to write every single line yourself. Modern programming relies on efficiently orchestrating the vast libraries of code already written for you.